Thank you so much, Wolf. And if I could have the slides. I was not initially on the program, so I am grateful for the insertion. I'm replacing some absent people. So I thought I would give you an overview of how much the field of brain imaging for humans has evolved. And this is based on my recent book, Seeing the Mind. I left a copy on the table so you can take a look. And so this is, unlike other talks, perhaps not so much based on my own work, although I'll speak about it, but also a review of what happened in the field. So this is a picture from the 16th century, actually, showing the phantasm that we may have for a long time of being able to view the thoughts of a person. This is an alchemy oven here, but we cannot, at the present time in the 21st century, help but see a sort of scanner that would scan the person and you would find the ideas flowing out of the head of the person. You can even see maybe the color of their underwear or the size of their underwear. So is this phantasm? Can we read the brain non-invasively? For a long time, we have to remember that the only way to access the human brain was to wait for the death of the person and to look at the anatomy and the lesions of the brain. This is the brain of the original patient from Paul Broca, which led to the definition of Broca's area. So you can see the lesion in Broca's area here. It's been rescanned recently, but this is the original anatomical, which allowed to do behavior and brain correlation, symptom-brain correlation. But of course, this was very coarse and very slow. And the revolution came with this paper in particular, 1988, so that's exactly 35 years ago, that Michael Posner and Mark Reichel and Steve Peterson and their teams were able to show that you could localize, to some extent, specific cognitive functions by having people lying in a positron emission tomography scanner and listening to words or seeing, reading words, speaking words, and you can see the big activation near Broca's area when you are generating verbs that are associated with words. This technique was primitive. I used it at the beginning. This technique required the injection of a small amount of radioactivity, which had to be generated on the spot because it was very fastly decaying. And you could make one image like one image per person, not like that. This is an average of several tens of subjects, but it required 15 minutes for one image. So that was slow and a little bit invasive, although the dose was very minimal. But all of these limits were completely blown out by the emergence of MRI. And today, when we want to look at the activity of the human brain, magnetic resonance imaging, functional magnetic resonance imaging, is the technique of choice, because it allows you to measure the whole brain activity at a resolution of a few millimeters or maybe 1 millimeter every second or every 2 seconds, whole brain, and do so completely non-invasively. There is no injection. The contrast agent is the blood itself circulating in the body. So, and these techniques can be very refined now. I'm showing you here a slide from the work of Jack Gallant in Berkeley and Alexander Huth. They're able to analyze people listening to stories and show that individual voxels in the brain, volume elements of the cortex, have responsivity to specific domains of conceptual knowledge. For instance, this voxel here seems to respond to social concepts, including people and their mental states. So this was done with a 3 Tesla magnet. Most labs in the world have a 3 Tesla MRI magnet, which has become quite standard also in hospitals. This is a high-level standard. But there are now commercial 7 Tesla magnets. And this is a picture from the 11.7 Tesla magnet, which is arriving in my place in Eurospin, south of Paris. So this is the world's biggest magnetic field for the human brain. This was 4 years ago. Now this magnet is installed and cooled by helium, and it is working. We are allowed now to expose a few human subjects for safety reasons at the moment to this high magnetic field. There seems to be no effect at all, so we will be able to run normal experiments with this magnet. And the goal when you increase the magnetic field is to get a better signal, and the signal can then be used in all sorts of ways. Not just functional MRI, but also looking at individual atoms, such as lithium, for instance, will become available with this machine. and also to look at the anatomy of the brain. So this is an image that was obtained on another 11.7 Tesla magnet. Now this is post-mortem, but these same images will be able to be done in vivo. And here you see a technique called diffusion tensor imaging, which allows you to look at the movement of water molecules, and through that, the nature of the membranes that impede the motion of water molecules, and therefore, in this case, the trajectory of the white matter. So the colors here indicate the direction of the fibers, and through tracking algorithms, you can get an idea of the connectivity of the brain. The beauty of this image is that with this high field and long acquisition times, this image is at the level of 200 micron isotope. It's probably the best current image of whole brain human connectivity. We still do not know fully the human connectome. It's still an open problem, and so this image can contribute to it. But going back to functional MRI, so functional MRI allows you to now localize at a finer and finer scale cognitive function. And with these high-powered magnets, the hope is to get to the scale of something like 500 microns in a routine manner. These images here are from the 7 Tesla magnet in Eurospin, and the point is that now each of these brains is an individual subject. The growing trend in the field is to look at single persons without having to average across subjects. And you can see that there are small patches of the cortex that are dedicated to particular domains of visual recognition, such as faces, or bodies, or places, or words, or objects. And we can localize them and find that there is a sort of universal organization in spite of individual variability. You can find such voxels in every brain. On the bottom is an image I borrowed from Florian Morman's work, so this is an introduction to Florian's work, showing that you can cross-validate in rare cases by recording from single neurons, and on the bottom is a single neuron responding to places. So it's showing that when you see fMRI activity selective for places, as you do in the parahippocampal place area, you can actually believe that this comes from single neuron activity, which is selective to the same domain. So in my own work, I study a lot the activity of reading, and this slide is also to show you that perhaps some of the most interesting work is to look at the education of the brain and how the brain changes with the acquisition of a particular culture and a particular education. So in this case, we and others have found that there are areas of the brain that get dedicated to a particular spelling system, particular alphabet, and respond very selectively just to words in the alphabet that you can read. And they will not respond to other matched stimuli, such as characters in another alphabet, or faces, or houses, and so on and so forth. The discovery here has been, we used to think that this was a big area, and this was a sort of banana-like area of 2 centimeters. When we now apply these new tools of high Tesla imaging, we see that what we thought was a single star is actually a galaxy, little patches of cortex that are highly selective. And in an individual brain, this can be very small, like a few millimeters, and respond extremely selectively. And as you can see here, also respond to the statistics of the stimuli. We have to think as the brain as a statistician that accumulates evidence. And in this case, when we have these stimuli that vary from completely irregular alphabetic stimuli all the way to real words or plausible words in English or in French, we can see that the patches of cortex respond more and more to these plausible stimuli. So the brain knows the statistics of the stimuli. We've been doing these experiments recently. This is from a paper from this year in bilingual subjects. Actually, the previous one was a bilingual subject in English and French. And in this case, everything is overlapping. There is no separate circuit that we can see for the 2 languages. But here, this is Chinese, English, bilinguals. And in most of them, we found that still there is a common circuit, which you see in green here, which responds both to English and to French. But there is also specialized patches that are just for Chinese. So if we scan Muming, I think we would find these patches in your brain, Muming. And there are still some surprises which you really don't understand. These patches that respond to Chinese also respond to faces. And we don't know why, except perhaps there is more similarity of the stimuli. So this is the sort of precision that we are achieving now, millimetric precision. but other people are able to do laminar imaging, which is also an interesting dimension. The cortex is not just a surface, but several layers, and we are beginning to be able to do imaging of specific layers of the cortex and ask about the function and the depth. So in my lab, we study a lot reading acquisition. So these are a few images of the things we can do. We were interested in what happens when you become literate. And so we scanned a range of people from pure illiterates that didn't have the chance to go to school, all the way to people who could read, and quantify their reading scores as the number of words they could read per minute. So 0 means complete illiterate. And all of the regions that you see in color grow in activity with literacy and allow us to track what happens when you educate the brain. So language areas become responsive to written language. Visual areas become selective for reading, and perhaps more surprisingly also, learning to read changes the phonological areas of the brain. Even the response to spoken language is being enhanced, almost doubled in people who have learned to read, and the connections between these systems are being enhanced. The point here is that there is an interesting mapping between the cognitive competencies that we educate ourselves with and the brain activity. We can read about 50% of the variance in reading scores by looking at brain activity at the moment. There is this correspondence. These techniques are becoming available for a while now in young children. This is a view of the mock scanner in the neurospin that allows us to train children to go in the scanner. And this can be done relatively easily in school-age children, starting around the age of 5 or 6, maybe all the way down to 4, but that's a bit challenging. You can explain to these kids that they are participating in an experiment, that they are little cosmonauts, and that they have not to move, of course. And then what you can do, this is an experiment we do with this plan, is to track individual children across time as they are learning. So here, this is one child learning to read. In France, when you enter school, this is the year where you learn to read. So we have 2 scans before school entry, and this child did not know how to read. And as soon as the child enters the school, we can see these 4 scans where we see the growing activity in the visual word form area, in the ventral visual cortex and in lateral temporal cortex. And this is quite compatible with what we think we know about the models of reading, the connection between vision and phonological representation. In a recent work where we have more subjects, we can begin to tease apart the variables, which honestly in human subjects is extremely difficult to tease apart causes and consequences because we cannot easily experiment for all sorts of ethical reasons. But here we were able to scan subjects with variable ages at which they acquired reading. And this allowed us to separate the variable of age from the variable of reading acquisition, and to show that for the visual word form area, it's really the acquisition of reading that counts, regardless of the age at which you learn to read. And it's quite different from the face area, which is just nearby. And the face area grows slowly in activity as a function of being exposed to faces over more years, basically, and continues to grow into adolescence. And so age affects the face activity, whereas teaching and entering school affects the reading circuit. And finally, I mean, we would dream to be able to understand how cellular responses encode the activity of reading. And of course, this is still very difficult because we do not have access to single neurons. Even if we got down to something like 400 micron voxel, there would still be about 1,000 neurons in a given voxel. And here it's more like several tens of thousands in the voxels I'm showing you. So instead, what we can do is rely on artificial neural networks models that are being recycled. Just like our brain is being recycled for reading, we can recycle these models of visual recognition and teach them to read. And when we do that, we find a lot of similarity to the human brain. We find that the artificial neural network will develop circuits that are specific for reading. So a few units will dedicate themselves to reading in these networks. And then we can analyze it and find a hypothesis about the neural code in human that we can then test in the actual brain. So we are doing this at this very moment. And we find that we think we begin to understand the neural code that allows us to recognize words. We think it's a code where there are units that care about a letter, for instance, the letter A, next to the space And space can be on the left, can be on the right. That gives you a positional code that says the first letter is A, or the second letter is A, or the last letter is A. And this code coming from both sides of the word gives a unique barcode, if you want, a vector code for a specific word. So we have an interesting dialogue between AI and brain imaging. You're trying to see to what extent the AI models reproduce what is happening in the actual brain. I'm personally still very critical of these AI models. I'm sure we'll discuss it more with Jean-Rémy's presentation in particular. But for the first, let's say, 200 milliseconds of brain activity, early visual recognition, we begin to have pretty good models, and maybe for other domains. Now, still looking at development, babies are being now an interesting target for brain imaging. This is already an old image that we did with Ghislaine 20 years ago, showing that babies of 2 months old have cortical brain activity, and in fact have specialized cortical activity. The baby's brain is much more organized than we used to think. And this is the activity during listening to language, listening to your mother tongue. You can see the circuit includes already Broca's area as well as the superior temporal region. This image is not very precise. 20 years later, it remains extremely difficult to get good images of the baby's brain for all sorts of reasons that you can understand. But people are getting much better at this. We just heard from a center in London, in UK, where they are doing specialized coils, specialized equipment for the baby to be comfortable and so on. Likewise in Yale. So we are seeing new images of the baby's brain. I think it's a very important frontier just for understanding this incredible machine of the baby's brain, but also to understand diseases at this early age, such as following prematurity and so on. So this is a beautiful image from Rebecca Sachs from MIT and her baby in the scanner. And on the right, you see some of the advances that have been made. So we understand that the infant brain already responds to language at birth and has specialized circuits for that. And the bottom image is showing that if you increase the amount of dialogue in which the child is engaged, at the age of 5 years, you begin to see differences in the way the brain is organized. So this is also a reminder that this organized brain needs input, educational input, from day one, and that we can make a huge difference. Parents can make a huge difference by talking to their children, and these networks will be changed. So, of course, we knew that before imaging, but the availability of the image makes a difference in being able to convince and convey this message to educators and to parents. One word about mathematics, because I think this is my passion also, to understand how the human brain can do science and mathematics, and we know very little about it. There are 20 times less studies of science and math in the brain than there are about language. So we need to do more. We begin to see that there are networks in the brain that are shown in blue here that respond whenever we do mathematics. And they are present in all of us when we do simple calculation, but they are also the ones that develop in high-level mathematicians when they think about very high-level concepts. But this is an area which is dramatically under-researched, and yet it's a very particular specificity of the human brain, how we are able to generate scientific concepts. So this will be, I think, an important area in the future. Now, I finish, I hope I'm not too long, by talking about brain decoding. If we understand the mapping between concepts and brain activity, we might be able to reverse the mapping. And from brain activity, to understand what the person was thinking about, was seeing, and so on and so forth. And there are many groups working on this topic. This here is one of the first such images that were generated by Bertrand Thirion in Neurospin, published in 2006, collaboration with my group. So the idea is very, very simple. You know that you have retinotopic map. So when you show an increasing ring or a turning wedge, you can see the corresponding activity move on this retinotopic map in the occipital cortex. That's what you see on the top of the slide here. And that means that whenever you see a little bit of activity in the map on the cortex, you can maybe paint a little splotch on the image and reconstitute the image. So that's what we did in the bottom. And you can see that the image which is reconstituted from brain activity looks a little bit like the original stimulus. You can see the expanding ring, or you can see the rotating wedge being reconstituting from brain activity. And in that paper, we're also able to show that when you just imagine a similar picture or imagine a letter T, we're able to project back the letter T and see it from brain activity. Now, this has become an industry, and there are many, many papers. This is a paper from just 4 years ago from the group of Kamitani and collaborators in Japan. What you see here is on top the image that the subject was actually seeing, and on the bottom, the image that was reconstituted with the help of decoding algorithms and AI. And on the bottom, you see the letters of the journal neuron being decoded one by one with the same algorithm. Here, people are not just using retinotopic maps, they are using any voxel in the brain. They are going beyond retinotopy, and so this allows you to add color, to add knowledge of the objects, and so on. But 2019 is just 4 years ago, but it's already a very old image. And so here is another image, and Jean-Rémy will show even more, I think. But this is the work of Rufin van Rollen and collaborators. And now with the help of additional AI techniques, they're able to reconstitute very realistic images of what the subject might have seen given the brain activity. So now on the column on the left, you see the actual image the subject was seeing. And on the right, you see for individual people or based on their average activity, what the AI algorithm was able to reconstitute. And I find just this completely amazing. You see a little cat showing the head next to the door, and the image which has been reconstituted is an animal sticking its head between two surfaces, very close to the original image. And you can judge for yourself. It seems to work remarkably well. So should we be afraid of that? We have to always remember that here the person was very actively collaborating with the experimenters. And without this collaboration, it would not work. So the collaboration involves several steps. First of all, to acquire enough data to train the algorithm. And second, to not ruin the image itself. It's very easy to ruin a brain imaging exam by moving or by thinking of something else and so on and so forth. So in my point of view, for the moment, at least these images are helpful to understand the brain and to understand that we understand the mapping, but they are performed with the help of the person, and in the case of clinical work, in the interest of the person. And it will be hard to move beyond this step. Without the collaboration of the person, none of this would be possible. Finally, these techniques, I showed you a huge magnet which weighed 130 tons, Revidat neurospin. This is a 500-kilo machine, which is being sold for a few years now, which is also a magnetic resonance imager, but now you can just plug in the wall and bring to the bed of the patient. So the technologies are changing very fast. This is based on sensors that can sense very low magnetic field. So the magnetic field here is much, much smaller, fraction of what it is in the bigger machines, but still you can do reasonable clinical images. You can see on the right, the top image is a classical, I think, 3D image, and the bottom image is the same patient visualized with this particular machine here. I don't want to advertise for it. There are several such projects being developed across the world. So this will be very important for pediatric imaging because you could be following the same child across hours, and this will be important just to follow any neurological disease. It will not be easy to do functional MRI with this, but for anatomical MRI, it will be very useful. And I don't want to give you the impression that MRI is the only technique around, so just one image to show that MEG, magnetoencephalography, and electroencephalography remain very important techniques for us to measure brain waves, brain activity as a function of time, and in this case, to decode also the presence of a particular picture, the presence of a picture of a face, for instance, across time. But Jean-Rémy will be speaking about that, I think, in the afternoon. So with that, I thank you for your attention.